we present non-Newtonian ViRheometry, video-based rheometry via similarity analysis. There are various fluid-like materials around us, like sauces for fries, pasta, and salad, or congee, or even cosmetic products. Many of them come with large-scale inclusions, for example, sesame in the sesame dressings, diced vegetables in sauces for a salad, diced tomato in a pasta sauce, and rice grains in congee. These large-scale inclusions are stationarily distributed in the material, and the material as a whole can be viewed as a homogeneous continuum. To reproduce their flowing behavior in computer animation, we need to know the relation between the strain rate and shear stress, called the flow curve. There are experimental devices called the rheometers to measure the flow curves. For an accurate measurement of the flow curve, they typically encapsulate the specimen in an extremely thin gap, which excludes materials with large-scale inclusions. Even for materials without large-scale inclusions, the measurement can be unreliable if the moisture separates from the material and the material slips over the moisture, like this mustard example. Instead, we use a video-based approach to estimate the flow curve. It is known that the Herschel-Bulkley model fits well to the flow curves of various fluid-like materials. So we estimate the three material parameters of the Herschel-Bulkley model. For a better matchup with materials whose flow curves can be reliably measured by a rheometer, we modify the previously used flow rule for simulating Herschel-Bulkley materials. Compared to the captured footage shown on the top, the simulated results using our modified flow rule together with the measured parameters offer a nice matchup compared to the previous method. We built our experimental device using off-the-shelf materials, with a downbreak configuration where we can change the width and height of the region for pouring the material. For an unknown material, we perform an experiment to record its flow. In our early attempts, we found that the optimization can pretty nicely match the recorded footage with the simulated result, but interestingly, the resulting flow curve may not match the measured one so well. This is because of the similarity relation between material parameters, where different sets of material parameters can reproduce almost identical flow for a given downbreak setup. By analyzing this similarity relation, we know that this similarity relation is setup dependent. Building atop this insight and deeper analysis, we propose a method to effectively propose additional setups for further pinning down the material parameters. Now, using experiments performed for two setups and doing optimizations trying to match up the simulations with the recorded footage, we obtain a much improved result. Here, we show the validation for materials whose flow curves can be measured by a rheometer. We see a nice matchup between the estimations and measurements. We show side-by-side comparisons between simulated and captured examples for a nozzle drop scenario. Note that our simulation does not account for the surface tension, so the surface looks bumpy. Nevertheless, the comparisons indicate that we can capture a couple of interesting effects due to non-Newtonian viscosity. With relatively low effective viscosity, Japanese thickened Worcestershire sauce forms a dip near the location of impact, whereas lotion, having higher effective viscosity, forms a lump and the material avalanches down the lump when flowing. Having much higher relative viscosity, we observe the coiling behavior for sweet bean paste. Now, we show applications of our method for materials with large-scale inclusions, so their flow curves cannot be reliably measured by a rheometer. Please refer to our main paper and supplementary material for the details of the experiments being performed and matchup between captured footage and simulations, as well as the estimated material parameters. When making the videos, we did not tweak any material parameters. We just plugged in the estimations from our method, which dramatically reduces the manual workload that was necessary for making an animation for a shear-dependent material. Thank you.